Well, it is a pleasure for me today to actually introduce Anna Fontcuberta in Morral for several reasons. And she's a full professor at the BFL, which has been all around the world, starting in Barcelona, then Paris, moving around all the way to California, Germany, and in Switzerland for now some time. And the reason why it's a special honor for me to introduce her is because I remember we've known for quite some time now, and I remember the first time I saw one of her talks at a conference, and was so inspired by her presentation on nanovirus at the time that I knew I had to work with her, basically. And that's why eventually I became a postdoc in her group. So she's known worldwide for her work on 3-5 nanowires and epitaxial work. She basically can make it look very simple to make nanowires that are decorated with quantum dots of a specific material composition, with a shell that can be asymmetric, just everything I think you can dream of a geometry and she can make it. And more recently she's been shifting or actually introducing new material systems, 4-type semiconductors, 5 semiconductors, and well, I think just to briefly say what she's done with them, she not only knows how to make them and make very creative different kinds of structures, but also how to exploit them for different kinds of applications, going from quantum optics all the way to photovoltaics. And I think without further ado, I would like to leave the floor to Anna. Thank you for being here, Anna.
I think people now expect a lot from me, so I hope I will not disappoint you. Yeah, I was very excited by the introduction. It's the first time I realized it when you said that solar energy has now become the cheapest form of energy. I remember my PhD time, people were discussing how we can get to $1 per watt, and now we got to the cheapest form. I mean, that's I just get. So very, very exciting times, and hopefully not only we get now to technical development, but we still can get some exciting scientific questions that we can tackle as scientists. So with that, we can combine excitement for science and also contribution to society. So I will talk about zinc phosphide and a bit our adventure to zinc phosphide as a earth-abundant material for absorbance in solar cells. I will start with a small reflection and trying to be a bit optimistic on the climate change. So. So these two people here are venture capitalists. In fact, they have been venture capitalists for a very long time. They also written books about how to lead, how to manage. And more than a decade ago, one of them, their daughter asked them, you invest in so many companies, you earn so much money, but when are you doing really something for us? When are you really doing impact? And this made him think, and from that time on, he started investing only in companies that will make a change for sustainability. And in that way, then he made up a plan on how we can reduce the CO2 content of our atmosphere. Not only the emissions, but how we can reduce it. And when you see here, this is his plan, and the plan, so the book is here, speed and scale, and it tells what we have to do from today to the next years to really remove the CO2 from the atmosphere. And the book has a lot of parts, so these are the main parts that it has, and he has a very detailed actions of what we can do. And so I think it's a very interesting work that he did, in which we can all see what part we can do, because we need many different kinds of ways of contributing to that. And today, hopefully, I will tell you, so photovoltaics, this helps decarbonize the grid, and also in innovation, because we need to innovate too. So if you have some spare time to read this summer, if you have a very long train trip, I would ask you, maybe that's a good read that you can have. So looking for trying to make a contribution, you see here this paper from Albrecht, in which he outlines, the different materials we have, and how close the materials are from the shock liquidity in efficiency. And as a material scientist, it's a very intriguing question why some materials work very well and some others we have a hard time making them efficient. It's not only the band gap that, the potential in absorption that plays a role, but there's something else too. And so in this graph here, you see that the king of the materials is gallium arsenide. It's a direct bandgap semiconductor. It has reasonable mobilities so that you don't have recombination. You have a very good material that can go. It's still, gallium arsenide is made of gallium. Gallium is, it's more abundant than indium, but it's very difficult to extract. So the cost to extract gallium are very high. Sometimes it's bound with indium gallium arsenide to make multiple junction solar cells. So certainly this is not the route we want to go because there's not enough of it in the Earth crust. So we need to find alternatives. And so the question I had is, can we have materials that are compound semiconductors, that are direct bandgap, that have a good carrier mobility so that we can extract the carriers, and that have the potential to be like gallium arsenide but in a much cheaper way. How people do this? So some people have different strategies. So one strategy is we continue using gallium arsenide, but we just use less of it. It is a reasonable hypothesis. With this you can reduce the usage by about 1,000 times. And there are different strategies that people do. Some people try to get high quality gallium arsenide on silicon. This is the work, for example, on the left. It is challenging because, as you see, gallium arsenide is made of 2 elements, and the order of the elements plays a role. It's not just an alloy, so you need to have bonds between gallium and arsenic. And if when you produce your material, at some point you have gallium or arsenic, then your material is basically dead, because this is a high point of recombination. So it's not that easy to have gallium arsenide on silicon as a cheap substrate. Other ways is you can have epitaxial liftoff, and this was the success of Alto devices, and the highest efficiency in gallium arsenide is from this company. Unfortunately, the company doesn't exist anymore. Alternatives to epitaxial liftoff are also what is called spalling. You start from a wafer and you can spall a piece of it, and this is very, very cheap, even cheaper than this. These are all alternatives to use very little of gallium arsenide. What we looked also for some time is to in fact, look at nanoscale gallium arsenide, because also if you look at a layer that is formed from these very nice nanowires, in fact, effectively you use very little bit of it. And here you're not restricted by what substrate you use. You can use a silicon substrate. You can even get rid of the substrate because you can put in a polymer and peel off the device. So in theory, that's a very good path to use very little bit of gallium arsenide. And as I will explain, this also has some advantage for light absorption. Still, we stopped doing this, and there are reasons for that, because I think this is probably not the way to go for real devices. This is a work we did with Esther some years ago, in which elucidates what are the effects that happen with the nanowires of 3/5. So not only you economize material, but there are also some effects that make you absorb a lot of light. And the experiment we show here, it's one of my favorite experiments, I have to say. So you put the nanowires in a solution, and you try to image them with a confocal microscope. And the confocal microscope is there to map where the photons are when you illuminate. And to do this, you have, in the solution, you have fluorophores that emit light every time they get a photon on them. And you can illuminate with different wavelengths, and with this you map where the photons go. This is one of the results. And so you see here around the nanowire, sorry, I have here, I'm still used to the pointer. So you have here a nanowire, and you see a lot of light close to the nanowire. This is the leaky modes into the nanowires that you see because they leak out a bit of the wire. Inside the wire, of course, we don't have fluorophores, so we don't have emission. And what you also see is that there is some light that disappears around the nanowire. So it's like creating a shadow of photons that have disappeared. If we do a cut here, we will see the leaky modes in the middle and a shadow that has developed around. So the photons have disappeared. What happens is that these leaky modes have a very good coupling to the wire, so you have very good photonic coupling to the wire, and this in fact makes you like suck all this light inside. And so this is very powerful, and that's why when you have a nanowire array in a substrate, it will be completely black, even though it's mostly empty. And so this is what made us try to use these structures for solar cells because of the good absorbance. This is a demonstration of a device we did. At that time, when we did this device, we didn't know how to do these very nice arrays there. In fact, when you look at this picture on the left with these nice arrays on silicon, in fact, it took us 7 years to understand how this can be done. everything takes time, so students have to scratch their head to understand what are the fundamental issues going through this. So as we didn't know how to do this, but we were able to get some wires grown on silicon vertically, we did a single nanowire device with a PN junction. So this is a scheme of the PN junction, and we have a P core of nanowire and an N shell, and we conducted the core through the substrate, the highly doped substrate, and the shell with a transparent contact on top. What you see here is the external quantum efficiency measured as for a nominal photon getting on the wire, how many electron hole pairs you create, and from the same build you have also the wire that is lying on the substrate. What you see, it's first you have very different numbers, and also the shape of the curve is very different. You see here that when the line nanowire you have very low absorption close to the band gap, while when you have a standing one you have a very high absorption. The highest absorption is close to the band gap, which is not typically what you have in semiconductors. You have usually very low absorption close to the band gap. You also see that per nominal photon you have 15 electron hole pairs. And this is not that every photon creates 15 electron hole pairs, is that in fact you're absorbing 15 photons because you collect these photons around. And so this was the first demonstration that this effect that we see, that the wires really collect all these photons around it. If you design them well, then it can be useful for photovoltaics. And this has kept us many years trying to get high efficient devices. And in fact, the people here in AMOLF and Eindhoven have the record devices. We can talk in the coffee break why I think it's not possible to go beyond this and why I think it cannot be produced in industry, but some topic to discuss later on. We stay on the positive side. So now looking at other materials, so I spent some time looking what can we do. So at the time I was doing this was 2015, there was the machine learning techniques for materials discovery were still not very well developed, so I had to look through all the literature, what materials exist, and I tried to look at this. So here, in this study here, you see already a study that tells you what are the potential of different materials that exist. And what you see here is how much electricity we would produce if we would use the production in mining for the elements that constitute the material, and we assume the shock requires efficiency for the materials, which we know it's not true. How much electricity we would be able to produce for the current production or the potential scaling up of production. You see the materials that can do the most are the ones that are here. So these are materials that have the higher potential in generating electricity. And I already highlight here zinc phosphide, which is one of the tops. You also have copper oxides. My inconvenience here is that they are not very stable. They tend to react one on top of another, and having different stoichiometries on a device probably is not a good thing. The same for the copper sulfide. Another way to look at this is you can look at the potential of your material to produce electricity, also in the extraction cost index. And this puts all the materials in different quadrants, and typically you would like to be in this quadrant here. And just for the note, silicon, crystalline silicon is here. And it's because of the high cost of purification. So if you do this and you look at the potential, you have iron sulfide that would be the best one. Everybody would like to have a device on iron because there's so much iron on the Earth crust. I think all devices that use iron, it's very, very low, and it's probably due to the iron likes a lot oxygen, tends to oxidize a lot, so this creates defects. So this is probably one of the things. So then we went to zinc phosphide, which is here. It's also new material. There have been some works in the past. We understood the challenges, but we thought we could go around them because science evolves, and we thought that the challenges that have been raised in the past are not a challenge in work today. So this is the crystalline structure of zinc phosphide. It's a tetragonal structure, which is very different to what we were used. We were used to cubic materials, so this is fun, and sometimes you have to scratch your head to understand what's going on when you have a TM. It has a good carrier mobility. The diffusion length is long. The band gap is 1.5 electron volts, so everything looks good for this material to do a solar cell. The challenges are that the thermal expansion coefficient is not matched to any substrate, and there is no commercial substrate that can match this. So it means that if you want to grow high quality material, typically we order the materials on top of each other on a substrate, and the materials that you put, they follow the same order. And if you don't have any substrate that the atoms can follow the order, then it's the problem, because it means you will have a hard time making crystal material. And I will tell you today how we go around this. So here is our machine. Our materials are done by molecular beam epitaxy. I don't expect molecular beam epitaxy to be in any production line of photovoltaics. This is not going to happen. But I think it's a very good material model system to understand how you can do material. Is a material good enough or not? What are the limitations in terms of the composition and everything. So this is for us a good model system. We evaporate zinc, and we evaporate P2 from gallium phosphide. And the reason is that phosphorus is a highly inflammable material, especially in the P4 form. And so typical molecular beam epitaxy machines with phosphor, they would have a big bucket of phosphor that they would evaporate and try to transform the P4 into P2. It made me very nervous to have a bucket of phosphorus in my machine. So what we do is we have gallium phosphide, it sublimates P2 directly, and the gallium stays in the cell, so like this, everybody is happier, including me, and the students too. So the way to go around the requirement of having a crystalline substrate that match the structure of your material can be do different. One way is you can start growing your material in nanoscale form, like we did with nanowires. If the footprint with the substrate is very small, then all these issues with the lattice mismatch and mismatch in the thermal coefficient of expansion, you can go around this because the stress that you create there is much less than when you have a large interface. This is one way. The other way is that you can just try to break this relation with the substrate by having a substrate that will not have any covalent bond. And this is typically 2D materials like graphene. So I will show you results on these two ways. So for the growth of graphene, we use commercial substrates because they're relatively cheap now. This is from Graphenia. You can have them on 4 and 6 inch substrate, then you can break your pieces and do your growth. They're reproducible, so like this, you know that each time you have the same substrate. If you do it yourself, it's not clear that your graphene will always be the same. And as you will see, we also buy them because they are not perfect. So they're reproducible but not perfect, and it's good to not be perfect. If you would have a full wafer like this with a full monocrystalline layer of graphene, and you would evaporate your material, because there is no covalent bond, the material would arrive here, it will wander around and dissolve. So nothing will happen. So it may eventually would happen if two atoms meet each other and then they would start creating an island, but nothing would happen. So it would grow for a long time and nothing would happen on your substrate. So having a polycrystalline substrate allows you to have some very little density of defects, but enough that you can start nucleating a layer. So this is the mechanism we propose. So you have a polycrystalline graphene substrate, and that has also some point defects, and so the atoms start sticking here, and then from this they create an island that evolves. And this is some scanning electron micrographs that show this. You can see very well the grain boundaries that are decorated by the initial stages of growth. You can also see that these flakes seem to be oriented in some way, even though they don't have a covalent bond. There is some kind of relation with the substrate. When you put them together, because you have grains, of course you don't have a monocrystalline layer, you will have a polycrystalline layer of zinc phosphide. And this is how it looks. It looks quite horrendous, especially if you're used to do perfect epitaxy materials. But what you see in the left, they still luminesce. They luminesce below the band gap, which means that there are the defects that are getting luminescence. But these are defects that luminesce, which is probably better than the ones that are not luminescent. So it's about 1.4 and 1.3 electron volts this is low temperature luminescence. Now why this is good? Having graphene, it helps the epitaxy, but also may help on making some devices. So first you can have your device on graphene, and because graphene is conducting, so and even though it's not covalently bound with your material, there is a very good conduction, so you can use the graphene as a back contact, and then you just need to put the top one. Or you can just transfer because it doesn't stick, you can just get your layers onto some other substrate and create your device. So it's also very easy to manipulate and to use to make devices. That's one of the reasons also to get it on graphene. Now, going back to the starting the epitaxy, the nanoscale, maybe we can go back to nanowires, and you know that I will not finish with nanowires because I already was negative about it. But I would like to show you that this is also a strategy to have high quality materials, and in fact, for fundamental studies, it's also interesting because it gets to know, we get to know the properties of this material that is not that well studied. So starting on the nanoscale, you can prepare the substrate in a way that you can foster the atoms to not grow on a layer-by-layer basis, but to grow vertically, and they start nucleating in an area. So what we did here, Simon, what he did here, he took a substrate, he exposed it to an argon plasma, very soft. This creates some defects, and there you would have a nucleation of the nanowires. That's how he did it, and you have this beautiful picture here. You have mainly vertical wires. Depending on the conditions, they can have different shapes also, depending how he does it. What was also interesting on this is that, in fact, by changing the conditions, which means the flux of the zinc and the phosphorus, we also change the composition, which is for a compound semiconductor, this should never happen. If you have gallium arsenide or indium phosphide, you should have 1-to-1, and if you start getting away from the 1-to-1 ratio, then your material is absolutely useless, is scrap. But here we see we can go to compositions quite flexible depending on the fluxes, and if we then look at the luminescence, we also see that the luminescence shifts depending on the composition that we're able to change. So it looks like it's a compound semiconductor, but quite interesting. It's probably that one of the elements, probably the phosphorus, changes the oxidation state, and this allows you to have a material that is still doesn't have these deep recombination centers. This is something that we still want to study, and this is one of the questions we still have to understand the material. But as you see, we change the band gap or the emission position, and this can also be useful for applications. We try to look at, so we use the nanowires, as I said, to understand the fundamental properties, and this is one of the advantages. So in this experiment here, we went to the SuperSTEM in the UK to look at the absorption coefficient in a different way that we usually do. So you illuminate the wires with an electron beam that is highly monochromatic, and you look at the laws of the energy of these electrons. And if you have a spectrometer that is high resolution, as they have, this doesn't exist everywhere, you can relate this to the absorption coefficient. You can do it by illuminating the center of the wire or in a grazing zone. And in the center of the nanowire, you will mostly have absorption through the bulk plasmons, what they call bulk plasmon, which is transitions at the more core levels of the elements. While if you go into the grazing zone, then you will have more the transitions that are close to the band gap. And this is what you see here. What you see here is that the measurements show a very high absorption here in the grazing zone, and you have many transitions here that contribute to absorption. I will explain later on what these are. Another way of looking at the absorption coefficient and to compare with different materials, and here also you need a nanowire configuration, is to measure absorption by measuring the change in temperature in the material when it's illuminated by different wavelengths. So in this experiment from Ehrler in Basel, she put the nanowires on top of a thermometer, and this is what you see here. This is a suspended microthermometer. You put it there, you illuminate, and you measure what is the change in temperature. Of course, you need to simulate a bit what happens to related to the absorption coefficient, but we compared several materials. And this was, in fact, also a collaboration with the TU Eindhoven, where there are also other materials from them. And if you compare gallium arsenide and zinc phosphide, what you see, you can look at the absorptance. So you see gallium arsenide, depending on zinc blend of Wurtzite, if it's parallel or perpendicular, you see the numbers, it goes from 3 to 4, depending on the polarization. With the zinc phosphide, it goes up to, the scale goes up to 25, the absorption is a bit less. So what we see is that zinc phosphide is about 5 times more absorbent in these wavelengths of interest than gallium arsenide. So not only we have a material then that uses earth-abundant elements, but also we can use many less of it, which means that you can, if you would have a thin film, it can be very thin, which means it doesn't have to be that pure. If you don't have to have an ultra-pure material. So the cost that you need to fabricate these materials go down drastically. One of the reasons for that is the band structure. So you have, here I compare the band structure of gallium arsenide and zinc phosphide, and the band structure on the left was simulated by one of our collaborators. What you see is in gallium arsenide, so this is the band gap here, and you see that there is one conduction band and the next one is quite far away. So these I put it in a similar scale so that you see it. And what you see with the zinc phosphide is after the band gap, you have many conduction bands here. And these are all the transitions that we saw in the electron loss spectroscopy. These are all transitions that are happening from the valence band. And this is what makes a very high absorption coefficient in this material. So here, we were just lucky. Nature has been nice to us when we chose the material. It has to happen sometimes. The next thing I wanted to talk, so starting a bit just beyond the nanowires, because I really think that this is not the way to get the industrially reliable devices. We started looking at other ways to nucleate at the nanoscale. This is just for fun. We started a subset that is covered with an oxide, and we offer some nanoscale openings, and we start to find conditions that the growth will only happen where there is no oxide. The oxide is a bit like graphene, atoms just go away. And so we see that we can have growth, crystalline growth on these steps here in an azimuthal dependence. We see what are the orientations that give the highest quality, and then you can, just for fun, you can make all these networks. Fun or not fun, I think there are interesting things to do this, but here it was just for fun to show that you can do nice structures. We saw really in these directions that these are single crystalline structures, which is quite interesting for us. So we went a bit beyond that to see can we use this for photovoltaics. So we started growing in a nanoscale hole, and you would think that if you have a mask that is, here's the oxide, and this is a nanoscale hole where growth starts, you would think that with this we want to grow a nanowire, but in fact we achieve something else. So when you look at as a function of time, what happens is you start having small islands going there and joining, and when they get out of the hole, they start creating a pyramid. And this pyramid is formed by surfaces that have the lowest energy. And here you see a bit later in time how this pyramid has formed. Then if these holes are close enough, then the pyramids will join. And that's what you see here. You have a highly textured material that is formed by these pyramids that form. If we now look at this structure in a cross-section TM, we see that they are, even though they started from islands that are decorrelated with each other, something happens when they join that they kind of agree with each other and it creates a single crystalline form. It's quite surprising for me from the epitaxial point of view. I would have never expected this. But they are single crystalline. And if you look at these joint structures, you see that for the grain that starts here is a single crystalline. You have some grain boundaries here. We think it shouldn't be too much of a problem because the carriers that you recommend, they should have to go through this path and they should not come to the grain boundary. Now, if we look at the properties of these materials, we see for the first time now, so we can also change the stoichiometry, as you see here, depending on the size of the hole, and they have room temperature luminescence. So the nanowires only have low temperature luminescence, the growth of graphene only low temperature luminescence. Here, for the first time, we have room temperature luminescence, which tells us that this is the material we need to use for the solar cell, so we are very optimistic. And now to finish even in a more optimistic way, here are some recent results. So we had the group of Albrecht coming this year, and we brainstormed on what would be the structure of the solar cell. And we were too much fixed on getting a PN junction, well, in fact, you don't need this. So you can try to think about a structure that you only need selective contacts. And this is, Stefan did simulations, and they told us what are the materials we can use. So we tried. This is the zinc phosphide. Unfortunately, we still use indium phosphide as a substrate. When we use indium phosphide as a substrate non-doped, then we have most of the absorption here. We use titanium dioxide as an electron selective contact, and then a transparent contact on top, and in the back we have gold. So in principle, you can absorb here, you can electron hole pairs, and they wander around. Electrons will go here, and holes will be collected in the back. And these are one of the first device characteristics that we show. So this is under low intensity illumination. Depending on the thickness of the TiO2, you see how you have an optimum with 10 nanometers, which makes sense. Below 5 nanometers, you don't have a continuous film. After 5 nanometers, you have. More than 20 nanometers, this has to be more resistive, so it doesn't work. So 10 nanometers is the best. When we illuminate under one sun, because we don't have any metal contact on top, they're still, the IV curves are not very beautiful, but still we have a 3% efficiency. So this is the first result, so yeah. this is why visiting friends, scientific friends, is fun because you can exchange. And this, we wouldn't have this if Albrecht and his group had not come to EPFL this year. So I'm very thankful for that. So this is my conclusion. So hopefully I convince you that being a scientist is fun. You can think about scientific questions that are of interest and have some applications. And here I have shown you how epitaxial methods can make a way towards high quality materials, that you can think about new materials and you can have ways of synthesizing them in high quality and produce devices. And zinc phosphide, in my view, is one of the materials that has a higher potential, and we will see in the next year. So now, before I finish, I need to thank the students in my group, because Esther was saying how many things I can do. I can do nothing. It's the students that do everything. So I'm really very thankful for them. They're a lot of fun and they're very smart. And of course the collaborations, and you for your attention.
Thank you so much, Anna, for this beautiful talk. Definitely met my expectations. And now the room is open for questions. Go ahead.
What should we scientists focus on to get this work from 80% to 20%?
For this material?
Yes.
So I repeat the question. So the question was, now we are at 3%, what do we have to do to get it to 20%? So we are, right now we are limited by the top contact. We see the series resistance is very high because we don't have yet a metal contact on top. We're working on getting this now. So this is one thing, and I think this will already increase the efficiency.
Perhaps you made a remark about that. So there happen to be no deep traps, I think you said. Is that true? Or
it's not understood. We
just God given,
we really need,
we should be pleased with that.
Yeah, so we recently got the project. Is not yet completely signed, but with Esther, and we have a theoretician that hopefully will help us understand the nature of these traps. So Nelson here, he already made some simulations on some of the defects we see, and we see the defects, in fact, they just create a reduction of the bandgap, a slight reduction, but it's slight reduction doesn't create a non-radiative combination. So it seems that this material, somehow, when you have a disorder or something, it doesn't create deep traps. One thing I didn't say is that this device I showed, we started trying this device with the worst material we have, which is polycrystalline zinc phosphide. And then we went to monocrystalline we were expecting better. In fact, not. The polycrystalline gives the better results. So there is something to understand there too, why a polycrystalline material gives you much better carry collection than the monocrystalline.
The composition issues, is a stable material, doesn't decompose if you change the stoichiometry a little bit? I'm happy to discuss how to measure the decomposition, but in principle it doesn't decompose. If you heat it more than 300, it will start decomposing because that's the temperature of deposition. But if you keep it at normal temperatures, then it shouldn't.
Thank you for your great talk. What's working? Maybe you can hear me like this. About 3 slides ago, you showed that the composition depends on the diameter of your holes. I was quite surprised about that.
Yeah, I can repeat the question.
But maybe, do you have an indication why this happens?
So I have a hypothesis why the composition changes on the size of these holes. You have, maybe I can go back to one of these. So you have the holes and the mask, and so you send phosphorus and zinc, and they all behave differently in the mask and in the hole. So they precipitate in the hole, that's where they stick, but they stay for a while in the mask, and some stay longer than others. And so it is the ratio between the two atoms is different depending on the size of the hole because you collect more or less of the thing around. So it's the interplays of these two masks, how they behave on the mask that affects this.
So you have surface mobility,
you have
absorption and surface mobility that transports the atoms towards the hole.
Yeah, so yeah, this surface, the transport, that is different depending on how much you collect and the size of your hole, yeah.
Thank you.
Other questions?
Thank you.
Wait, so, I just turn it off.
Yeah, thanks for the super nice talk. I'm wondering if you measured PL quantum yield to get out Fermi level splitting for the different polycrystalline and single crystalline layers to get an idea of what the potential is.
Yeah, no, we didn't do this. We didn't do this. And the polycrystalline has very little light emission at room temperature, while the monocrystalline has much higher. So it is very intriguing.
But that indicates maybe it's more of a contact issue or something with the device geometry and not so much the...
Yeah, I'll be happy to
But
discuss
yeah,
this.
we can talk more, yeah.
Just thanks a lot for the great presentation. Just following up with Urian's question regarding the size of the hole and how the pyramids are grown there. Could you elaborate a bit more about the physics, why the growth acts like this, like depending on the size? I see that, yeah, the size defines how which material, for example, is rich or deficient. But could you elaborate a bit more why this happens, or it's still unknown?
Well, maybe one easy way to say this is that the vapor pressure of zinc and phosphorus is very different. So when they arrive on the substrate, one will tend to desorb much easier than the other, and this the easiness of desorption, it is also even more different on the mask than on the substrate. So in the hole, when they arrive, I would say most of it will stay, while in the mask, most of the phosphorus will desorb, while the zinc may wander around and get into the hole. So you create an asymmetry because one material is more collected than the other. And so you have your growth here, and you have a certain region around it that you will collect. And of course, if your hole is very small or very big, this plays more a role or less of a role.
Yeah, thanks for the great talk again. So it's amazing it grows so well, but actually, and the crystal quality is so high, and you're only left with these grain boundaries. Are they exactly matching with the period of that structure, or are they even growing bigger, sort of assembling into bigger grains?
So if you make very big holes, you would create you can make a monocrystalline region that is much bigger, and we thought this would be better, which at least for the devices we need to still check, but it looks like it's worse.
Okay, and you said in the end, grain boundary recombinations may be not a problem if the carriers diffuse straight up and down. I guess that depends on how strong the fields are inside.
Yeah.
Or do you maybe already know that the recombination rate is not so high at the grain boundaries, like in CITS or CCTS?
This is one hypothesis. So one maybe answering to we did pump probe terahertz measurements on polycrystalline, monocrystalline, and the lifetime is longer for the polycrystalline than for the monocrystalline. Monocrystalline is very, very short. No.
Okay, great, thanks.
Which is all around, 3-5.
Interesting.
Yeah.
Other questions?
So the luminescence is brighter, but the lifetime is much shorter. Is that what you just said? Did I understand that right?
Yes, but because the other experiment is pump probe terahertz spectroscopy.
Yeah, okay. You're not looking at the
You're
luminescence lifetime.
No, exactly.
Yeah.
You look at the lifetime of the carriers that you photogenerate.
You haven't done PL lifetime, I guess.
No, we haven't, and because for the polycrystalline it's too low, so
Yeah.
yeah, you collect too little photons.
Thanks.
Good. Then, if there are no other burning questions, of course, you can always find her around today. But with that, I think we should thank Anna again.